In an hour, okay. So, so here's the idea by Aaron. The basic idea of the order. So there are three different orderings that are standard orderings. There's degradation, okay, which is so we're talking about my setting here, binary input, memoryless output symmetric channels, but some of them is not constrained to binary. But there are three different orderings. The kind of simplest one and most common one is degradation. Okay, and degradation is just the concept. You take an input, okay, then you have some channel output, and now if you can take that channel output and map it further to something else, which no longer depends on the input, but forms a Markov chain. You have input, then the first output, then the second output that only depends on the first one. Then that channel here, which is just further processing of the original channel, that's what's degraded, okay? And so if things are ordered by degradation, many things go nicely. For example, if you take a channel and you do map decoding and you have any code, and you first look for the decoding under one channel that is upgraded with respect to another one, then the upgraded one has better error probability than the other one, okay? So degradation stays preserved by map processing. So that's a very nice ordering and is used a lot. So I didn't mention it, but in all this spatial coupling, all this relies on degradation if you go to general channels. And then there's more noisy and less noisy. That's also in nice order. And then there's more or less capable. And more or less capable, it's quite easy. So you have two channels. A is more capable than B. And all this means is that if you're looking at the mutual information, so maybe I should first say that A, they both have the same input, and this goes, let's say, to Y, and then maybe B has also this input, and it goes to, let's say, Z, right? Then you have I, so the A goes from X to Y, okay? And so if this is bigger equal to the mutual information between X and Z. And so, of course, if this was just for the standard input distribution, the maximizing, that's just the capacity, right? But we're asking this should be for all joint distributions P, X, Y, Z, which have the form, you first have the PX. So the important thing is here that you can choose, this has to be true for all input distributions, not just for the maximizing one. And then that just means these are the two channels. Okay, so it's important that this, if this was only true for, let's say, for the binary input channels and symmetric channels, the optimizing input distribution is always a half. And so if this was just for the, let's say, the binary case where the input distribution is half, then this would just mean that one has more capacity than the other one. Okay, so that's not what we're meaning here. They could have the same capacity, but if for all other input distribution, one is always more informative, has more capacity than the other one, that's what is meant with more capable. And so that's a notion, an old notion. I actually don't know who introduced this notion, but it has been useful in many other contexts. But what Aaron said is the following. So you have, again, you have A is more capable than B. You have a code C, and you do map decoding. So you do optimum decoding. Then if you're looking at the probability under A, so the one that's more capable, the better one, right? Then you want to say that that's better than the other one. So the bound doesn't quite say it's better, but it says it's not much worse, okay? So it says that it's at most n times PB plus the binary entropy function of PB. And so if B is very small, then basically it says it's just at most n times worse than this. And because of that, what I said before, and if you now take a code, so take, so if this and the other thing that is also proved, this might have been proved already at some other point, is that B is C is least capable of all binary input memoryless output symmetric channels. So if you think of all the standard ones, the BEC, the BSC, the binary additive Gaussian noise channel, etc., the BSC is the worst, okay, of the same capacity. And hence, if we go back to what we said beforehand, if you now construct a polar code with under successive decoding that achieves capacity or is arbitrarily close to capacity, its error probability will go down. So if you pick a polar code for BSC, right, under successive, then you know that its error probability can be made as small as the error probability can be made as small as e to the minus square root of n, and there are constants around, but that's the order, right? And hence, if you plug in here e to the minus square root of n, right, then that still goes down essentially like e to the minus square root of n, and this you can also forget. So you see that now for any other channel, this will also work. Now, of course, this is under map decoding, okay? So the code was constructed for successive, then it of course works also for map, for PP, and then it works for any channel. And so this, I'll skip. If you look in the thesis of Aaron, it's about 1 page. It's not, I mean, it's not impossible to prove, but you know, it's just a little bit some calculation. This one is even easier. So if you look up in general, right, so if you look at the relationship between error probability and mutual information, then you will see, so on the one hand, you have the Fano inequality, right? So what do you get here? The log of the alphabet size minus 1 times p plus h2 of p. So that's the Fano inequality. So, you know, again, you have some, this comes from an alphabet, this is the observation, that's the mutual information, and you want, and the p is under map, you know, you're finding the best decoder, and so what's the relationship between them? That's just Fano, and this thing here is basically just the following relationship. First, think of the binary case, right? In the binary case, this is just this will look like the binary entropy function, right? This thing here, right? In the binary case, the entropy is just something like this, depends on the distribution that you have, right? And so this is 1 here, and around here, a half, it's here. But what is the error probability? The error probability is the min of the two things you have, right? So the error probability just looks like this, right? And so that's just a statement that if you take the binary entropy function, you can inscribe this triangle in here, right? And that's very easy. And if it wasn't binary, then the entropy, if anything, can just get larger, right? If you take a distribution on a large alphabet, the error probability will still stay the same, but the thing will be even larger. So that's fairly clear. And so now, if we know this, then the proof is just 1 line. So how does it go? So we're taking PA, and we're using this one here. So this is X, so we're thinking of X1n, so this is block code Y from 1 to n. So this is for the A channel. So let me just make sure that I get this correctly. So for the A channel, that's the more capable, right? So now the claim is that that's smaller equal than h of x 1 to n and z 1 to n. I'll come back to it in a second. So this is now for the B channel, okay? And so here we're using the fact that it's more capable. Come back to it in a second. And now this here, this is, you know, we are working from 2 to the n. So this whole thing, I'll just take n here. And now this thing here is just the error probability for the B. And so the only thing we have to check here, right, what does it have to do with more capable? Well, of course, the I of x and y is just the h of x minus the h of x given y, okay, and the I of x, okay, and so this we're saying is bigger equal than the than this one, which is just the h of x minus the h of x given z, right? And we cancel this one, and we see that that this one, I hope I get the, is this correct? Yes, okay. And so we're taking this, right? So from this we get then that h of x and y is smaller than h of x and z. No, it just means that if you're taking it a half, if we're talking about binary input symmetric channel, it just means that if you're taking the input distribution where it's a half, it means they're all the same. So these curves all meet, but that for all other distributions, one curve is always on top of all the other ones. Okay? It's just some normalization. Okay? But clearly, a BSC cannot be worse than whatever, some other channel, you know, if I take a BSC with very small error probability, cannot be worse than some, let's say, the binary erasure channel with erasure probability 1, right? So, I mean, you have to have some comparison. Okay? Good. Any questions? So I think this is a, you know, this is quite a nice theorem because it, you know, this is quite general. And so it tells us that that quite generically all we need to do is to prove something for the BSC, and once we do this, then we are fine, and we know that essentially universally, as long as we can prove that the error probability goes down faster than 1 over n, that this will work everywhere. Okay. Good. So now let's try to talk a little bit about generalization. So in principle, right, this theorem tells us that makes our life much easier because we just need to look at the BSC. And so why does this still cause trouble? Now so we're talking about, let's say, still Ried-Müller. So all we need to think about is now this, right? Now, in principle, it's still nice, right? Why is it nice? Because clearly for the BSC, we still can think of, you know, as we did for the block thing, we can still think of bits being flipped or not, right? So we can still think of something like vectors W, which are whatever, right? We can think of the error pattern. Right, so that's quite nice that we can think of error patterns. So it still makes sense in principle to think of things like this omega here, and you could think of the set of error patterns in here, and you could hope that something very similar than what we did for the BEC works, right? Like if we had, for example, do this for the Gaussian, then it wouldn't be even clear how we even start the formulation if we want to stay in this discrete thing, because we're going to get real numbers, right? But here, at least, you know, the beginning, actually, these are patterns of 0 and error patterns, right? So, you know, what would be natural to do? Well, it would be natural to do, for example, to compute log likelihood ratios, right? Of whatever, you know, we have the I guess I call it Ci given right, so it would be natural to compute log likelihood ratios, right? And so these log likelihood ratios would be then, if I'm assuming you have the all zero code word, right? If this Li would be bigger than 0, right? Then this means I would decode correct, right? And if this is smaller than 0, it would mean I make a mistake, right? And so, so this is the optimum decoding, right? I compute the log likelihood ratio here, right? And so I can, of course, write this down also as the sum log of all the code words. So this would be all the code words in the code such that Ci is equal to 0. And this is over all the code words that are equal to 1 at this special position. And so this would be the optimum decoder for the ith bit. And now I could see if I decode towards, you know, if we decode correctly or incorrectly. And so we might maybe then put, if, for example, this, perhaps then, this depends, of course, on this pattern here. Okay, then perhaps we put this, okay, I call this now Z. This is very bad notation. Sorry, let me just change everything here to be consistent. And so if that was the case, then perhaps, you know, if it's a mistake, then perhaps I want to put the W into my set, the small omega into my set omega, and then I could imagine that I now do something very similar than what I did beforehand, okay? Now, the first problem is like the following. If I take a pattern like this, and I get some number, okay? So I take, let's say, so I take W, and then I compute the Li of W. And so now I take maybe a W tilde, okay? And the W tilde might be the same W, but perhaps I'm just now taking another position here, and I'm also setting this to 1. So I'm adding one extra error to it, right? Then unfortunately, so I now do this, right? One extra error. And now I'm computing the Li of this other pattern with one extra error to it. Unfortunately, it's not true that this thing is monotone. Okay, so there's, you know, monotone you could think of now maybe in two ways. So, you know, you would assume that if I have more errors, that this would become more negative, right? I mean, or at least would go closer to 0 perhaps, right? But unfortunately, it's not true, okay? It's very easy to find counterexamples where if you make maybe a mistake computing the ith bit with a certain pattern. Now you add one extra error to it, right? And you actually get it correct, this bit, okay? Now, of course, this is not true in average, right? So in expectation, we know that if I'm thinking of the two channels, then I could think that I first sample according to some parameter, and if I now randomly pick an extra bit and flip it, right, so that I will get in expectation more errors, and I'm looking at the expected distribution. So I would look first at the distribution from this one here by picking according to some particular BSC P, and I would get some distribution perhaps of this log likelihood ratio. And then now I would look for a BSC P prime, where P prime is bigger than P, right? Then, and so I get another distribution. Then I know that, and that's what we said before, and I know that this channel is degraded with respect to this channel, and it means that this distribution, because map decoding preserves degradation, this distribution must be degraded with respect to this. So everything we compute, like error probability, Bhattacharya constant, capacity, anything you want, any reasonable functional that can be expressed by some, you know, something that has a particular form, all of them must be monotone with respect to it. But the monotonicity is with respect to the expected value. The monotonicity is not pointwise. And so what this means is that what you in general will have is you will have, it's going to look like a Swiss cheese, okay? Swiss cheese can be good, but in this case, unfortunately, it's not good, okay? Because you can have holes. So it could be that here you can decode, here you cannot decode, and suddenly you can decode again, right? And now remember Russo's inequality. Russo's inequality said, well, it's just a flow, so you have flows here. But now you would also have to take into account flow that's again going out, right? So in some way or the other, you would have to show that things are still essentially monotone or more monotone than not monotone, okay? But nobody has been able to make that precise, right? So that there are not too many holes in there. And so that essentially once the weight goes in there, that things would, would more or less stay in there, okay? So the first problem is, from L is not monotone. And when I say not monotone, I mean not monotone pointwise. There's a monotonicity in expectation, but there's not a monotonicity pointwise. Okay, so that's not very good. There's another thing that's kind of annoying about this channel, and that's the following. Recall what happens for the BC. For the BC, the parameter of the BC only played one role. And the role is how likely it is that we're choosing every particular erasure pattern, right? So if I change the parameter, I'm not changing anything. I'm not changing the criterion whether I can decode or not. I'm just changing the probability of picking certain things. I'm more likely to pick things with more erasures. That's the only thing that this plays. Unfortunately, that's not true here. If you look again here, right, if you look at this formulation here, then the parameter, let's say P or epsilon, whatever we pick, plays two roles. Number one, which error pattern we pick, right? The higher the P's, the more likely we pick error patterns that have roughly n times P errors. But it, unfortunately, is also directly in the criterion itself, right? The log likelihood itself contains the P here too. Is that clear? So when I'm changing the P in the Russo inequality, it assumes that this set is fixed, right? So we have already a problem that this looks like a Swiss cheese. But we have another problem is that there is no such omega that is independent of the channel parameter. Does this make sense? Right? Whether or not I can decode a particular error pattern does not just depend on the error pattern, but it is also a function of P. Okay? Now, the dependence is not super strong. I mean, you would assume that, again, you can prove something that essentially doesn't matter. But unfortunately, it's still there. Okay? So, omega is a function of P also, or of the channel parameter. And then there's one final, perhaps even more annoying things. All these things you can kind of deal with, and that's the following. If you think of the BEC, and you do a flip from being able to decode to be able not decode, right? Then this is quite a fundamental change. So in particular, if you think of the associated log likelihood, okay, so the log likelihood would go from being able to decode, you have infinite, this corresponds to having infinite log likelihood, to jumping to 0. Okay, so it doesn't matter if you represent it as log likelihood or a difference of probabilities, but there's a large jump. Okay, every time there's a change, if there's either it stays or it makes a big jump. The problem is that if you're dealing with things like the BSC or Gaussian channel or any other one, and you're looking at and you're getting for something, you're getting maybe this parameter here. Okay, and now you adding an extra error to it. Okay, the first problem we said is that we don't know that this necessarily goes in this direction, right? It could sometimes even go in this direction. But even more annoyingly so, we don't know by how much it goes. There's no prior bound, okay? In particular, if n goes to infinity, etc., this could move arbitrarily little. Versus here, this moved a lot. Why is this important? So you can think of this procedure of adding one extra noise to it as like kind of a degrading procedure, right? You take a channel, you have an error, and now you degrade it by adding extra errors to it. Now, it's not very hard to see that if you degrade a channel, right? And so this means you first take an input, then you get a certain output, and now you degrade further, that if you have sufficient movement, okay, so if you knew that any time you do something, it would have to jump by at least some delta, where delta could be arbitrarily small but fixed, okay? You wouldn't even need to know that it moves to the left or to right, since you know that in average things are degrading. If you know that things in average are degrading, and so that the relationship between degrading, and you know that the movement is reasonably large, then you know that from here to here, this must have gone down, the capacity or whatever must have gone down by something that's related to this delta, okay? But if I can't tell you by how much, this all depends on, is a function of delta, and actually depends like the square of the delta, so the relationship between here and here, the degradation or the loss in capacity depends like the square of the delta. If you can't give me a bound on the delta, then there might have been lots of like little movements here and there, okay? But you don't know that this actually became worse, okay? And so, there are many ways of trying to fix this, but so far, nobody has been able to somehow solve all the three problems together, and so we don't have any bound. Now, there are many other ways you can think about it. As before I already said, you don't have to think, you can think of any quantity. You can think of the bit error probability, you can think of the extrinsic bit error probability, you can think of the bit error probability of the randomized decoder. If things jump, they all have to jump together, okay? So even if you couldn't show that this jumps to an error probability of half, just even to show that it jumps to something would already really be nice, okay? So there are many, many quantities you can think of. There are many ways you can represent it. We have looked at probably dozens of these different setups. Something is still missing, okay? So I think the first open problem that would be really nice, if someone could come up with an idea of how to prove, or how even just to show that there's any jump, okay? Perhaps once you show there's any jump, perhaps there's some other arguments that show that the jump cannot be too small. Okay, let me just mention now a few other open problems, if I find them. Okay, so let us go back to spatially coupled codes. The way the proof goes, and the way I explained it, is there was a lot of randomness in these codes. If you remember, the way I drew these things is that we had all these different codes lined up. And then the randomness that we had in there was that, the one that was easiest to prove is that for each of these edges within a certain window, you could choose where to map it to, right? You had a certain profile. And so, basically for each of these nodes here, you have to have, and for each of these edges here, there's one of degree of randomness, right? So if you think about it, in theoretical computer science, there's this notion of de-randomization, right? I showed, we didn't go through the whole proof, but we showed that almost all the codes in this ensemble are very good. But now if you wanted to find one, right? So the notion of de-randomization would be now to find one. Now if you had only very few bits, right, you could just go through them, and it would be very easy as long as you can check. But since you have lots of degrees of freedom, it's like the degree times the number of variable nodes, that's the degree of bits that you need to describe one. This will be hopeless trying to de-randomize them. So the question is if there are such codes that still have the same behavior, but are much simpler, have much less degree of freedom. And so one extreme case you could think of the following is you could just think of sparse, just standard sparse convolutional codes. So you could have in general for a convolutional code, how does this in general work? Well, you can have in general whatever k input streams. So you have, I'm thinking of a feed-forward convolutional code. You can have whatever k such input streams. And so now you can have a certain number of output streams. And so you could either have the output streams or you can think of the parity check view. So in the parity check view, you would simply have now a certain number of checks. And so, maybe this check would just, take maybe one branch from each of these, or maybe in some two of them or whatever, would be certain checks here, and you would have several of those, right? And whatever, maybe this is your convolutional code. So you have here maybe k is equal to 4 input streams, and you have 2 of these checks, right? So this would define a rate a half convolutional code. Is that clear? So we have 4 streams. And then what will happen, each of these check, you have to think of this check and then one moved over, etc. Right? Just think of a standard time-invariant convolutional code that you have, right? And so since we have here 2 constraints per time and 4 inputs, we would have still 2 outputs that are there, and that would be a standard time-invariant convolutional code. Okay, so we know that such a code, in general, can be decoded optimally with a Viterbi algorithm. But what is the complexity of the Viterbi algorithm? You basically have to look at, you have to basically look here at a window that would contain all these, the branches here, like this, and so on, right? And then the complexity, unless you find something smart, there would be just 2 to the, the state space would be 2, if this is all binary, 2 to the number of variable nodes that you see in there. That would be the complexity of the state space, right? So very soon, even in this case, this might be whatever, 12 or something like that, or 16, like, maybe in 20 like this. So we would have a state space of 2 to 20, and that's not a big convolutional code. So now, okay, so in general, Viterbi algorithm, you can do for this. But what happens now if maybe the state space, if this is now huge, right? So pick this to be maybe, 1,000. Pick maybe this length here, to be very large, right? Would be completely impossible. But it turns out that if you pick this very large but still keep that sparse, right? Then this is exactly the same thing that happens for standard codes, right? Any standard code has this Tanner-graph representation. So any standard code has a representation of this form that I always drew. What's special about LDBC codes is that this thing becomes large, but the degrees stay constant, right? And so if this thing becomes very large, but the degree stays constant, then iterative decoding becomes a reasonably good method, depending on exactly what the structure is, and you no longer need to do map decoding. And so the same thing happens here. If you take this, where this you make now huge, but you keep the degrees constant, okay, then you can again do iterative decoding. So suddenly iterative decoding becomes something reasonable to Viterbi. And if you then, in addition, then, since the state space is so large, the initial, whatever it's called, the initial state is not forgotten, okay, or not forgotten for a long time. That's exactly when the spatially coupled, you can think of this now as a spatially coupled code, in which this thing is not forgotten, in which you will get close to maximum likelihood performance, okay? So even though it would be completely impossible to run a Viterbi algorithm if this is 4 times 4,000, 2 to the 4,000 states, but if you run now with this just a BP algorithm with a standard termination, then actually this becomes good, okay? It becomes essentially capacity achieving. So now if you do this, you have almost no degrees of freedom, right? Because the only degrees of freedom you have is where these things, now your ensemble is just, maybe these 2 things or 3 things and where these things connect, right? So it's very different from something like this. The question is, you know, can you still prove anything about codes like this? You can empirically run it, behaves quite well, right? It might be a good alternative for practice, but the question is, how much randomness do you need? Okay, can you get away with very little randomness like this? And then you basically get back to something that's almost, you know, essentially constructive, okay? At least if you had a constant number of terms here, computer scientists would call this constructive because you can de-randomize it, okay? And so you would, and even in practice, this might actually be attractive codes because structures like this would be very easy to implement in any hardware, right? Much easier than something like what I had originally, where all these things are irregular. So imagine in hardware, that is much easier, right? Because you have an extremely regular structure, okay? So problem number 2 would be to what degree you can get rid of randomness in the construction, and perhaps what would be the limits of getting rid of the randomness so that you can really do with much less, okay? Okay, and maybe the final problem. We spend a lot of time talking about things like Reed-Muller codes and whether they achieve capacity or not. But this is really just, you know, let's assume they do, and let's assume you could even prove that the scaling was perfect, and this would be your dream codes. That still wouldn't be very helpful if you can't find a good decoding algorithm. And so the question is there any way to do decoding efficiently, close to these limits? Of course, we know, I mean, there's some algebraic ways of decoding them, some majority logic decoding, etc. But these are not, you know, these are not competitive. And so the question is, could you do anything? And so if you think of, and again, this is unfortunately only for those that know polar codes a little bit, and it's the same picture that I drew before. And if these are now the order of this whole matrix in the polar thing, and so then what we have is, right, then we have some positions that are, let's say, you know, there would be some positions in here that would be, let's say, polar positions. And there are some other positions, and I'm not drawing the ones that are frozen at all. And there would be some other positions that are maybe Reed-Muller positions. Right? And so some of them will be common, but some of them unfortunately will not, right? So if, for example, and so the question is, can you use any weighted structure, and what could you use, right? So we know that for polar codes, there's not just successive. There's also, of course, list decoding. You can do BP decoding. And you can do many other tricks. So, so there's not just one order of how you can do successive, but there are actually log 2, capital N, factorial orders of how you can run a successive decoding algorithm. And where do these orders come from? They all come from when you take the small n is log 2. You know, these are the bits, so these are, if for each of these positions you can take a 0-1 sequence, you can take a 0-1 sequence to describe what these things are. And so you can take any permutation of these indices, and that's again a valid polar code. Okay, so you have lots of degrees of freedom. So it means you cannot just write one such polar decoder down, but you could write down, you know, these small n factorial polar decoders. And you know, you could try, for example, for the BC, a very simple thing would be to simply start going down and see if in any of them you make some progress, right? And if in any of them you make a progress, you can decode and then you can exchange between them, right? So what is the problem? The problem is that you might encounter at some point such a thing like this, for example, which is a Reed-Muller position, but not a polar position. What does it mean? It means that under successive decoding, this is not a reliable position. If you simply go down, right? The polar code, the successive, will not be reliably able to tell you what it is, according to it, but you need to decode it, right? And so how could you hope to jump over this? Well, if these positions were very nicely interlaced, that wouldn't be a big problem, right? Why wouldn't this be a big problem? Because you could use a list decoder, right? And then simply, if you get there, you simply split into two branches. Guess, think of the BEC, let's say. Guess it's either 0 or it's 1, go down. And then hopefully at some point, maybe you need to split it here one more time. But at some point you would get to positions in which you know what the value is, but you can actually reliably decode it. And so you would hope that this same thing happens as what I had told you for the Maxwell decoder, that now you have many branches of the decoder, but now you will actually be able to decode this bit that you had previously guessed, and only some of them might be compatible. Okay, so perhaps some of them, these branches will predict that this is a 0, some will potentially it's 1. And if this, let's say this is 0, and this is 1, and this is 0, and this is 1, but you know that this bit is 0, right? Then you can take away these two branches, and the list size again shrinks, right? So if you had things that were very nicely interlaced, perfect, right? You would be able to decode easily. Unfortunately, this is not true. Unfortunately, it's almost the opposite. Almost all the Reed-Muller positions which are not polar come in the beginning, and then you get all the polar which are not Reed-Muller, okay? So this means, and you have a lot, right? I told you that the intersection is a fraction, so I think if you transmit at rate c, I can't remember, either the intersection is 1 minus c or the intersection is c, okay? So, but, you know, essentially you get a linear number of such positions that you first had to guess, and since this would be a linear number position you had to guess, you would have an exponential size of the decoder that grows linearly in the block length, and that's, you know, that's not very useful, okay? Okay, so people have tried all kinds of combination of stringing together, list decoding together with all kinds of permutations and many other tricks. For small lengths, you can perhaps do it, but nobody has really found an algorithm that would work for, let's say, length 1,000 and let's say a Gaussian channel and to decoding close to the maximum likelihood decoder. There might be one other viewpoint. Again, it looks intriguing, but it's not so clear. So think first of the BC. And so do the following. Let's assume you have a code defined, but at the decoder, I don't tell you what actually the code it is that you have defined, okay? So at the decoder, I first run for all the positions from 0 to n minus 1, and simply denote all the possible words that are compatible with what I have seen. Okay, so the meaning, if for example, at this position, this is frozen, my code, I'm thinking of right now, let's say of I'm thinking, it doesn't matter, it could be a Reed-Muller code, okay? And let's assume this one I haven't picked. Then when I run through the decoder, I don't actually use that fact, okay? I'm just writing down all the compatible code words. Now, in principle, you can do this for the BC because the set of all the words that are compatible with what you received will form a linear subspace. So even though you have the subspace, you know, the number of words in there is exponential, you can describe it very compactly, right? You just need n whatever the number of generators you need the dimension of the subspace. Is it clear? So you could just run down. Every time you don't know, you know, what this is, if it's 0 and 1, you just keep both of them. And so at the end, you can describe it by just giving me a set of generators for this subspace, right? And so what you could do is for the BC, you first run through, you just get me these generators. There's an easy way to do this. And now you know that at certain position, this has to be, let's say, 0, because these are frozen. This simply corresponds now to certain positions here to being 0. You have to solve this small linear set of equations, and you get the solution, okay? This could be already slightly more efficient than solving this system of equations initially, because this system could be smaller. But the point of this is not that. The point is the following. If you now do the same thing, not for the BC, but let's assume you do it for the BSC, there's a curious nature of the polar decoding itself, right? The curious nature of the polar decoding itself is that essentially all the positions here polarize, right? So it means even though the channel is, and what is a polarized channel? That's a BEC. Is that clear? Because polarized is either you know exactly or you know nothing. So even though the channel itself is not a BEC, these things here, okay, like, I mean, as a thought experiment, look like a BEC. So if there weren't these channels in between that are neither, you know, there's this sublinear fraction of channels that are neither polarized nor not polarized, right, that are somewhere in between, then it should be that the set of kind of words that are still compatible, kind of typical with what you have seen, okay, with the observation, should still form something that looks kind of close to a linear subspace, right? Unfortunately, there are all these other channels in there, you know, there's some sublinear fraction in there, and so I don't know how to get rid of them. But if you could do this, right, you could again run this, get the whole subspace, and then do this, solve a linear system of equation and be done, okay? Again, looks like you should be able to do something, but we don't know how to actually do anything. Okay, CB, do I have to give you some money back if I end now, or? I think it's fine. Okay. So then, thank you very much again for all attending, and I'm done, okay?